Hello all, welcome to the class of Discrete Mathematical Structures 18CS36. Today I'll be teaching a topic in Module 5, Introduction to Graph Theory. The topic name is Vertex Degree and Handshaking Property. Myself, Dr. Madhura, Assistant Professor, Department of Mathematics, Sai Vidya Institute of Technology, Bengaluru. We'll first know the definition for vertex degree. Suppose G is a graph, then the number of edges of G that are incident on the vertex V with the loops counted twice is called the degree of the vertex V, and it is usually denoted by dEg of V or D of V. V is the vertex of the graph G. Suppose we want to find the degree of the vertex V, then we count the number of edges incident on that vertex, and when we are counting so, we count the loops twice. That gives us the degree of the vertex V denoted by D of V. The degree of the vertices of a graph arranged in non-descending order is called the degree sequence of the graph. So we have the degrees of all the vertices of a graph, and if we arrange them in non-descending order, then that gives the degree sequence of the graph. The minimum of the degrees of vertices of a graph is called the degree of the graph. So whatever the minimum of the degrees is obtained, that gives us the degree of the graph. Example, we consider this example, this graph with 4 vertices V1, V2, V3, V4, and we'll write down the degree of the vertices. So degree of V1. Degree of V1 is 3 because 3 edges are incident on the vertex V1. Degree of the vertex V2 is 4 because we observe 4 edges are incident on the vertex V2. Degree of the vertex V3 is 4. There are 2 edges incident on the vertex V3 and there is a loop. Whenever we are counting at the loop, it is counted as twice. So 2 times, degree is counted 2 times. So this gives us degree of V3 is equal to 4. Then degree of the vertex V4 is 3 because there are 3 edges incident on the vertex V4. Therefore, the degree sequence of the graph is 3, 3, 4, 4. We are arranging in non-descending order, so that gives the degree sequence. And the degree of the graph is 3. The minimum of the degrees gives us the degree of the graph. So here the degree of this graph is 3. Next, we'll know about isolated vertex, pendant vertex, and pendant edge. A vertex is an isolated vertex if and only if its degree is 0. So if the degree of any vertex is 0, means no edges are incident on that vertex, means we say such a vertex as isolated vertex. A vertex of degree 1 is called a pendant vertex. So if suppose only one edge is incident on a particular vertex, then that vertex is called pendant vertex. An edge incident on a pendant vertex is called a pendant edge. So the edge which is incident on that vertex whose degree is 1 is called a pendant edge. Next, we'll learn about regular graph. A graph in which all the vertices are of same degree k is called a regular graph of degree k or k-regular graph. So if the degree of every vertex is same and it is equal to say k, then such a graph is called as regular graph of degree k or Alternately, it is called as k-regular graph. Example, suppose I consider a square which has 4 vertices here. Observe that degree of every vertex is equal to 2. Degree of every vertex is 2 because 2 edges are incident on every vertex here. Another example here, we can observe in this graph, degree of every vertex is 4. 1, 2, 3 and the curve here. So 4. Loop is counted twice. So degree of this vertex is also 4. So this is a 4 regular graph. We take another example wherein degree of every vertex is 3 here. So this is a 3 regular graph. Another example wherein here also degree of every vertex is 3. Difference between C graph and the D graph is the graph C has 10 vertices and the graph D has 8 vertices, wherein the degree of every vertex of both these graphs are 3 only. The graphs shown in figure A and B are 2 regular, 4 regular graphs respectively. A 3 regular graph is called a cubic graph. Means wherein the degree of every vertex is 3, those graphs are called as 3 regular graphs, which are nothing but figure C and D. The graph shown in figure C is a 3 regular or cubic graph, and this particular cubic graph has 10 vertices and 15 edges. And there is a special name for this, having 10 vertices and 15 edges. Such a graph is called Peterson graph. The graph shown in figure D is a cubic graph with 8 vertices, wherein the 8 can be written as 2 cube. And this particular graph is called 3D hypercube and is denoted by Q3. It is having degree as 3 and can be represented as 2 cube, which is equal to having 8 vertices. And the graph D is known as 3D hypercube and denoted by Q3. In general, for any positive integer k, a loop-free k-regular graph with 2 power k vertices is called the k-dimensional hypercube or k-cube and is usually denoted by qk. So any k-regular graph with 2 power k vertices. So here we observed this was 3 regular graph with 2 power 3 vertices. That is why this is denoted by Q3. So in general it is k regular graph with 2 power k vertices is called k dimensional hypercube. And it is usually denoted by Q suffix k, Qk. Handshaking property. The sum of the degrees of the vertices in a graph is an even number and this number is always equal to twice the number of edges in the graph. Suppose G is equal to V comma E, the vertex set V and the edge set E. Then this is symbolically represented as summation degree of V, where V belongs to the set vertex set V, is equal to 2 times the number of edges. Cardinality of E represents the number of edges in the graph. A very important property. So whenever we write down the degrees of all the graphs, the sum of the degrees of all the graphs is always an even number and that number is always equal to twice the number of edges. So summation degree of V is equal to 2 times of cardinality of E. The proof for this property is obvious because while counting the degree of the vertices, each edge is counted twice, once at the each end. So that is the reason this becomes 2 times the number of edges. This property is called the handshaking property because it states that if several people shake hands, then the total number of handshakes must be even. Because 2 hands are involved in any handshake, the total number of handshakes must be even. And since it is related to a handshaking of persons, then that is the reason it is named as handshaking property. We'll move ahead with the important theorem in the concept of handshaking property. In every graph, the number of vertices of odd degree is even. Proof. Consider a graph with n vertices. Suppose k of these vertices are of odd degree, then the remaining n minus k vertices are of even degree. There are totally n vertices in the graph, out of which we assume k vertices are of odd degree. Then the remaining n minus k vertices will be of even degree. Let us assume the n vertices are of the form v1, v2, v3, etc. vk, vk plus 1, vk plus 2, etc. up to vn. So there are totally n vertices which are represented by v1 to vn, out of which we are assuming there are vk number of vertices also in the middle, vk plus 1, vk plus 2, etc. Now let us assume v1 to vk be the vertices of odd degree. That is what we assumed in the previous step, that k vertices are of odd, remaining n minus k vertices are of even. So we are assuming in that v1, v2, v3, etc. up to vk are the vertices of odd degree, and vk plus 1, vk plus 2, etc. up to vn, the remaining n minus k vertices are of even degree. Then sum of the degrees of the vertices, all the vertices, is equal to sum of odd degree vertices plus sum of even degree vertices. So the left hand side was sum of the degrees of all the vertices, and that is equal to, we have split into odd degree vertices plus even degree vertices. So we are taking the sum of all the odd degree vertices and even degree vertices. We call this expression as 1. In view of the handshaking property, we have the sum on the LHS is equal to twice the number of edges in the graph, and the sum is always even. The left hand side is nothing but the sum of the degrees of all the vertices, and by handshaking property this is equal to twice the number of edges, which is representing an even number. So left hand side is a even number now. The second term, the sum in the RHS of equation 1, the second term is nothing but the sum of the degrees of vertices with even degree each. So degree of every vertex in the second summation is nothing but even, and hence when you add up all the even numbers together, the sum is again even. So what happens? The first summation in the RHS of equation 1 must also be even. We already know the LHS part by handshaking property is an even number. The second summation, which is nothing but the sum of the even degrees, is again even. So the first sum in the RHS of equation 1 must also be even. That is, degree of V1 plus degree of V2, etc. up to degree of Vk must be even. Because I takes the value from 1 to k, we are substituting I equal to 1, 2, 3, etc. up to k. So we obtain, and expanding the summation, we obtain degree of V1 plus degree of V2 plus degree of V3, etc. up to degree of Vk is equal to even number. But from the assumption made, that is V1, V2, V3, etc. up to Vk are all vertices of odd degree, the star equation I'm talking about. So from this assumption, each of degree of V1, V2, degree of V3, etc. up to degree of Vk are all odd. So therefore, number of terms in the LHS of equation 2 must be even. That's because odd numbers, when we add up even number of times, we get the resultant as even. So we have all these as odd numbers, odd degrees, no? Degree of V1 is odd, degree of V2 is odd, degree of V3, degree of etc. up to degree of Vk is also odd. So we have sum of the odd numbers. So when we add up these odd numbers, the sum can be even only when we have even number of odd numbers. So odd numbers existing even number of times, only then the sum will be even. So that is the reason k must be an even number. Hence, we have proved the resultant. Now we will move on to problems. First question. Can there be a graph with 12 vertices such that 2 of the vertices have degree 3 and remaining 10 vertices have degree 4 each? If such a graph exists, then find its size. Size means number of edges in the graph. So it is given that there are 12 vertices in such a way that 2 vertices are of degree 3 each and the remaining 10 vertices are of degree 4 each. So applying the handshaking property, we will be able to recognize whether such a graph exists or not. If such a graph exists, then we need to find the size of the graph, that is number of edges in the graph. Solution. Sum of the degree of the vertices we will calculate first. So which is equal to 2 into 3 plus 10 into 4. Because there are 2 vertices of degree 3 each. So every vertex is multiplied by its degree plus remaining 10 vertices have degree 4 each. So remaining 10 vertices are multiplied by its degree. So 2 into 3 plus 10 into 4, which is equal to 46, and we observed it is an even number. So according to handshaking property, if the sum of the degrees of the vertices is equal to an even number, then such a graph exists. And to find the size of such graph, we apply the handshaking property that sum of the degrees of the vertices is equal to twice the number of edges. So we have sum of the degrees of the vertices as 46. So 46 is equal to, we don't know the number of edges in the graph. That is what we have to find if such a graph exists. So we write it down as 2 into cardinality of E. Simplifying, number of edges in the graph is 23. So thus there are 23 edges in the graph of the desired type with 12 vertices, in which there are 2 vertices of degree 3 each and 10 vertices of degree 4 each. So the size of such a graph is 23. Second problem. If a graph with n vertices and m edges is k regular, then show that m equal to k into n divided by 2. Second part of the question. Does there exist a cubic graph with 15 vertices? So firstly, with n vertices and m edges having degree equal to k, degree of every vertex equal to k, firstly we have to prove that m equal to k into n divided by 2 satisfies. And once we have proved it, the second part of the question is to show that whether a cubic graph with 15 vertices exists. Third part of the problem is, does there exist a 4 regular graph with 15 edges? Means if the degree of every vertex is 4 and having 15 edges in the graph, then we have to show whether such a graph exists or not. Solution. Given that the graph G is K regular, it is given in the first part of the problem that The graph is a k regular graph. Then the degree of every vertex is k. Therefore, if G has n vertices, then the sum of the degrees of the vertices is n into k. In the previous problem, we did it know. If we know the number of edges, number of vertices in the graph, and if we know the degree of every vertex, which is nothing but k here, then sum of the degrees of the vertices will be product of those two. Number of vertices into its degree. So that is how we got n into k. By handshaking property, this must be equal to 2 into m. Suppose G has m edges in the graph, then applying the handshaking property, sum of the degrees of the vertices must be equal to twice the number of edges in the graph. So that is why this should be equal to 2 into m. Symbolically, we can represent it as n into k equal to 2 into m. Sum of the degrees of the vertices is n into k is equal to twice the number of edges by handshaking property, so 2 into m. Simplifying this, we obtain m equal to kn divided by 2, which is the required answer of the first subpart of the question. Using the concept of handshaking property, we have proved this resultant. Second one, if there is a cubic graph means three regular graph, that is degree of every vertex is equal to 3 with 15 vertices. It is given in the data that it has 15 vertices. Then the number of edges it should have is m equal to kn divided by 2. Just now we have proved that resultant. So if suppose I have a cubic graph or a three regular graph with 15 vertices, then the total number of edges in it must be of the form m equal to k into n divided by 2. Here k value is 3 because it is a three regular graph, and n value is equal to 15. The total number of vertices in the graph is 15. So we substitute the same thing here, which gives us 3 into 15 divided by 2, which is 45 divided by 2. We are talking about number of edges in the graph. So that is m. M cannot be 45 by 2. Number of edges cannot be a fractional number. So since this is not an integer, we conclude such a cubic graph with 15 vertices does not exist. Our question was to verify whether such a graph, that is cubic graph with 15 vertices, exists or does not exist. So since we obtained a non-integer value for the number of edges, we conclude that such cubic graph with 15 vertices does not exist. Now the third part of the problem, we have to verify whether a graph which is 4 regular graph with 15 edges exists or not. So it is a 4 regular graph. So degree of every vertex is 4. That is k equal to 4. And there are 15 edges in it. So m equal to 15 is given. So let us find out the number of vertices in it. So given a 4 regular graph with 15 edges means k equal to 4 and m equal to 15. Then the number of vertices it should have is n equal to 2m divided by k. We obtained the resultant for m as n into k divided by 2 in the first part of the question. Using the same concept, we are just simplifying for n and writing the formula. So n equal to 2 into m divided by k. Substituting m and k here, we obtain 2 into 15 because there are 15 edges divided by k value is 4 since it is a 4 regular graph. So this on simplification gives us 30 divided by 4. Again, this is not an integer. So hence we will conclude that a 4 regular graph with 15 edges does not exist. N is nothing but the number of vertices in the graph. Again, it should not be an integer. Total number of vertices should be a positive integer in the graph. Since we obtained 30 by 4, a non-integer value, we are concluding that a 4 regular graph with 15 edges do not exist. Next, determine the order of the graph G equal to V comma E in the following cases. We have to obtain the order of the graph. That is nothing but number of vertices in the graph, where V is the vertex set. So number of vertices means N, or cardinality of V we have to obtain in the following cases. First case, G is a cubic graph with 9 edges. So given graph G is a cubic graph, means it is a 3 regular graph having degree of every vertex is equal to 3, and there are 9 edges in the graph. Second case, G is regular with 15 edges. So it is just mentioned that it is a K regular graph. We can assume degree of every vertex is K, having 15 edges in the graph. And thirdly, G has 10 edges with 2 vertices of degree 4, and all other vertices are having degree 3. So there are totally 10 edges in the graph with the condition that 2 vertices are having degree 4 each, and the remaining, that is 8 edges. Remaining vertices means we don't know number of vertices, no. So remaining vertices are having degree 3. Solution. Suppose the order of the graph is n. We assume there are totally n number of vertices in the graph. Since G is a cubic graph, a 3 regular graph is nothing but a cubic graph. All the vertices of G have degree 3. It is given, it is a cubic graph. So it has degree equal to 3 for all the vertices. Therefore, sum of the degrees of the vertices is equal to 3 into n. When I want to take the sum of the degrees of all the vertices, I multiply the total number of vertices into its degree. So degree of every vertex is given as 3 into total number of vertices in the graph we have assumed as n. So that is why 3 into n. By handshaking property, summation degree of V equal to 2 times of cardinality of V. That is same as reading sum of the degrees of the vertices is equal to twice the number of edges in the graph. This gives us 3 into n. Total number of sum of the degrees of the vertices, we have found it to be 3 into n. So left hand side is 3n is equal to twice the number of edges in the graph. There are totally 9 edges in the graph from the given data. So it is 2 into 9. So simplifying this, we obtain n equal to 6. Means the order of the given graph, which is a cubic graph with 9 edges, its order is equal to 6. That is, number of vertices in that graph is 6. Second sub question. It is given G is a regular graph with 15 edges. So since G is a regular graph, then the degree of all the vertices is equal to, say, K. According to the definition of regular graph, degree of every vertex must be equal to same. Say it is equal to K. It is given there are 15 edges in that graph. Suppose the order of the graph is n again. There is total number of vertices we are assuming as n. Then the sum of the degrees of the vertices is equal to n into k. N is nothing but the number of vertices into its degree. Degree of every vertex is k here, because it is given it is a regular graph. Assumed to be k regular graph. Again we apply handshaking property. That is, sum of the degrees of all the vertices is equal to twice the number of edges. So there are totally n into k. Degree of sum of the degrees of the vertices is nothing but n into k. N is the number of vertices into its degrees k, equal to twice the number of edges. The number of edges in the graph is given as 15. So what is n from this? N can be written as 30 divided by k. Since the degree of all the vertices is not known to us, that is k is not known to us, but we know that it is just a positive integer. So it follows that n must be a divisor of 30. So we will now list out all possibilities that exist for n. So 30 divided by 1 gives us n is equal to 30. 30 divided by 2 gives us 15. So n is equal to 15. 30 is divisible by 3 as well. So 30 divided by 3 gives us 10. So n equal to 10. 30 is not divisible by 4. It is divisible by 5 and 6. So it gives us 30 divided by 5 gives us 6. 30 divided by 6 gives us 5. So like that we are writing all possible orders of G. So n takes, that is number of vertices in the graph, takes all these possible orders. Since k was not given, degree of every vertex was not known to us, it exists to be more number of vertices are different possibilities existing in it. Third one, suppose the order of the graph is n and it is given that two vertices of G are of degree 4 and the remaining n minus 2 vertices are of degree 3. This is the given data for us, that there are two vertices whose degree is 4 and the remaining, totally there are n vertices, so remaining will be n minus 2 vertices of degree 3. Again by handshaking property, that is sum of the degrees of all the vertices is equal to twice the number of edges. We obtain 2 into 4 plus n minus 2 into 3 is equal to 2 into 10. That is, there are two vertices of degree 4. So that is the reason 2 into 4. Vertices are multiplied by its degree plus remaining n minus 2 vertices. There are remaining n minus 2 vertices whose degree is 3. So vertices is multiplied by its degree. That is why we obtain n minus 2 into 3 equal to twice the number of edges. The number of edges in the graph is given to be 10. So that is why 2 into 10. We'll simplify this and obtain the value of n. So on the LHS we obtain 3n minus 6 is equal to 12. Simplifying the constants we obtain this 12, which gives us 3n is equal to 18 or n is equal to 6. It is number of vertices in this graph which has 10 edges and out of which 2 vertices are of degree 4 and remaining are of degree 3. Satisfying these conditions, the number of vertices in the graph is 6. We'll see next problem. For a graph with n vertices and m edges, show that small delta is less than or equal to 2m by n less than or equal to big delta, where small delta is the minimum and big delta is the maximum of the degrees of the vertices. There are two notations here. representing the degrees of the vertices, small delta and big delta, right? So small delta represents the minimum of the degrees of the vertices and big delta represents the maximum of the degrees of the vertices. We have to show the result that small delta is less than or equal to 2m by n less than or equal to big delta, where m is the number of edges in the graph and n is the number of vertices in the graph. Let us assume d1, d2, d3, etc. up to dn are the degrees of first, second, third, etc. up to nth vertex respectively. Means we are assuming degree of the first vertex is 1, degree of the second vertex is d2, degree of the third vertex is d3, etc. up to degree of the nth vertex we are assuming as dn. Then by handshaking property, sum of the degrees of the vertices is equal to twice the number of edges. Now sum of the degrees of the vertices means d1, d2, d3, etc. up to dn are the degrees now. So we are going to add them up. So d1 plus d2 plus d3, etc. up to dn is equal to 2 into m, twice the number of edges. Number of edges in the graph we assume to be m. So that is why 2 into m. We'll call this as equation 1. It is given that small delta is the minimum of d1, d2, d3, etc. up to dn. It is mentioned that small delta is the minimum of the degrees of the vertices. So degrees of the vertices are assumed as d1, d2, d3, etc. up to dn. So small delta represents the minimum of all these. That is, delta is less than or equal to d1, small delta is less than or equal to d2, small delta is less than or equal to d3, etc. up to delta is less than or equal to dn. Since this is the minimum of each of the degrees, we use the notation less than or equal to. Now we add up all the LHS and all the RHS part. So we are adding deltas in the left hand side and we are adding right hand side. This is all less than or equal to d1 plus d2 plus d3, etc. up to dn. Here we are adding delta n times. So small delta added n times gives us n into delta in the LHS part, and this is less than or equal to d1 plus d2 plus d3 up to dn by handshaking property is equal to 2m. Using equation 1, we have this RHS sum d1 to dn is equal to 2 into m. So simplifying this, we obtain small delta is less than or equal to 2m divided by n. Let us call this as equation 2. If we observe, we obtain the LHS part of the required inequality. That is, small delta is less than or equal to 2m by n we have obtained. Now we need to arrive at big delta is greater than or equal to 2m by n, or equivalently 2m by n is less than or equal to big delta, where big delta is nothing but the maximum of the degrees of the vertices. So in a similar manner, we will be able to prove the resultant for the RHS part of the required thing. So it is also given big delta is the maximum of the degrees d1, d2, d3, etc. up to dn. That is, since it is the maximum, we can use the symbol as greater than or equal to. So big delta is greater than or equal to d1. Big delta is greater than or equal to d2. Big delta is greater than or equal to d3, etc. up to big delta is greater than or equal to dn. Because this big delta is nothing but the maximum of all the degrees. So that is why we can symbolically write it down as greater than or equal to. Again, we will add all the LHS part and the RHS part. So delta added up n times in the LHS is greater than or equal to d1 plus d2 plus d3, etc. up to dn. So we are adding the big delta n times. We obtain adding it n times. It is n into big delta greater than or equal to, I have written as it is, the sum in the RHS using handshaking property from equation 1 is 2 into m. d1 plus d2 plus d3 etc. up to dn is nothing but the sum of the degrees of all the vertices, and by handshaking property this is equal to 2 into m, which we have already quoted in equation 1. So we can write it down as 2 into m. So simplifying this, big delta is greater than or equal to 2m by n, which is equivalently writing down as 2m by n is less than or equal to big delta. So we have obtained the second part of the inequality in the required resultant. So we'll just call this as equation 3. Now we are clubbing equations 2 and 3. So combining them, we'll be obtaining the required resultant. Small delta is less than or equal to 2m by n, which is less than or equal to big delta. That's the required answer for us. So I've given some practice questions for a better understanding. So these problems are also applications of handshaking property. You can try them, which will give you more idea on the same topic. Thank you for watching.